Hello, Gen Chem friends. I hope you're doing well today. So in previous videos, we discussed and did calculations with respect to the Bohr model of the atom. The Bohr model of Niels Bohr's atomic theory stated that electrons in an atom can occupy only certain energy levels, and that those electrons can move from lower to higher or higher to lower energy levels by either absorbing or emitting energy. And Niels Bohr was able to use his model to explain the atomic emission spectra for hydrogen, which is great, and it's got him the Nobel Prize. But there are all these other beautiful elements in the periodic table. They all have, each of which have their own unique emission spectra, which is listed here on this periodic table. And so looking at the emission spectra for particular elements, you quite quickly see that there's no clear, obvious mathematical explanation for when you get elements that have more than one electron. These elements down here, they've got plenty of electrons. Why is there no emission spectra there? That points to the need for another model or another theory as to where an electron is in an atom and what its behavior is. So that additional model that we're going to use in conjunction with the Bohr model of the atom is this model that deals with quantum mechanics. Quantum is just a fancy word that speaks to a pocket of energy. We used it when talking about photons. But when we use this term quantum mechanics, it really is a fundamental shift as to how electrons behave and how they are arranged in an atom. In the Bohr model of the atom, particularly hydrogen, we saw electrons as particles. We are now going to see, as part of the concepts of quantum mechanics, electrons can also have behavior as waves, like light. And because of that, there is some uncertainty of electron position in an atom. We will talk about that with regards to the uncertainty principle later, but let's talk about this concept of electrons as waves, not as just particles. We alluded to that a little bit when we talked about electromagnetic radiation and how electrons have properties of light with regards to energy. But what experiment was done that really solidified the concept of electrons behaving as waves? That was done in 1927 with this double slit experiment. This isn't talked about in your online homework, but I wanted to share it with you because I think it is an important piece of information to add to the quantum mechanical model of the atom to explain or to prove why electrons do behave as waves. So in this double slit experiment, in a very crude way, you can think about if we had a bunch of particles and we somehow hurtled them towards a detector screen. But in between the particles and the detector, a way to somehow take a picture of where those particles went, we had a slit with openings at particular places. If we had a sample that behaved solely as particles, when we would hurl them toward the detector, we would only see a picture of those particles that lined up where the slits were, because we wouldn't expect to see any particles where there was a partition between the particles and the detector, because the particles can't go through. So this first diagram you see on the left is what you would expect to see if your sample behaved entirely as a particle. Conversely, if you had a sample that behaved as a wave, like light, if you were to take that sample and project it toward a detector with a screen in between the wave sample, the light sample, and the detector, those waves are still going to propagate, and through constructive and destructive interference, give you a pattern similar to what you see in the middle here, where you would see lines, detector lines, at particular places on the screen, not just where the slots are, but where constructive and destructive interference happened between the waves. So that's what you would see if you had a sample that behaved solely as a wave. So now, so what happens if we have a sample of electrons that we know are electrons? And it turns out that the pattern that we get is similar to what you would get as a wave. You see markings that happen in distinct regions similar to particles, but those, you see the patterns in places where there are no slots, where you would expect to see constructive and destructive interference. So the take-home point from this double slit experiment is to add evidence to the fact that electrons can behave as a wave. Yes, they can behave as a wave due to this double slit experiment. But we also know that electrons can behave as a particle from that photoelectric effect experiment we talked about previously. So, are electrons a wave? Yep. Are they a particle? Yep. We can use both wave aspects and particle aspects to explain electrons and similarly explain fundamental aspects of matter. That kind of blows, I remember that really blew my mind when I was a chem student. It still blows my mind now. We can think of matter, all matter, as having wave-like properties and particle-like properties. So those are the important tenets, or that is one important tenet of the quantum mechanical model of the atom. In the next video, we're going to do calculations with regards to wave-like properties of matter using an equation that came from the double slit experiment.